My name is Jeff Fair. I have a PhD in Material Science and Engineering from the University of Minnesota. I have a BA in Physics from Brigham Young University. I've worked with solid-state reactions. I've worked characterizing materials, semiconductor materials, thin films. I currently do a lot of work with nanoparticles as well as solid-state reactions. The way I got involved in 9/11 research was about in 2005. I had read Steve Jones' paper on, his initial paper on why the buildings collapsed that day. To give you a little background, on the day of 9/11, on September 11th, I was actually in Albuquerque waiting to, I had an appointment at Sandia National Lab, which is part of Kirtland Air Force Base. And that morning, a colleague of mine knocked on the door and said, as I was getting ready, he said, a plane just flew into one of the Trade Center towers. And I thought, that's strange, and continued to get ready for our appointment. A little while later, he came back and said, a second plane flew into the towers. And then I thought, okay, this is not just your ordinary news day. Something's going on. So I went out to the lobby of the hotel, and people were watching the news. We all watched what happened. Obviously, the base, Sandia is part of Kirtland Air Force Base, so we knew that we weren't going to be getting on the base that day, and sure enough, the base had locked down. No civilians were going in. So we got a car and drove back to Salt Lake City. So the news of the remainder of that day is a little hazy for me because I wasn't sitting in front of the TV watching the news. And I wasn't aware of Building 7 until I read a Steve Jones paper in 2005, which talks about Building 7, talks about the strange details and evidences of, surrounding Building 7. And that's what really grabbed my attention and made me want to look more into this. And so I actually looked for Steve Jones, and I sought him out, and we talked for a little bit. I wanted to get a feel for his sincerity and his motivation for doing this, and so we talked a little bit, and then I watched one of his talks that he gave in September of 2005 at Brigham Young University. And we talked some more, and at that time I was working as an electron microscopist. I was characterizing materials, and I thought that I might have something to offer if eventually he was to come across some evidence, or evidence was sent to him. And so I offered what I could do to study that and to get some data on any of the evidence that he might collect. So eventually, he was able to get some metal samples that were from some of the steel beams from one of the towers, and we studied those. I cut up some of those steel samples and polished them to see what we would find in the steel. Some of the pieces that he acquired at the time had some corrosion. They'd obviously gone through some melting, and we thought that those might be significant. So we actually were looking, and I was going in that direction. That's sort of my expertise, solid-state reactions, and that's not quite solid-state necessarily, but that's certainly in the realm of my expertise. So that's the direction that I wanted to go, was to look at these materials, study the phases, and maybe see what temperatures that these phases would have to, or the temperatures that the steel would have to get to create these phases. And then around 2006, I believe it was, Steve started receiving dust samples and started looking at these dust samples. So the study of the metal samples turned up different phases. I did obviously see the steel phase and iron oxide phases. We did find an iron sulfide phase as well as an iron silicate phase. looking at all the phases, I came to the conclusion that in order to create these phases, we'd have to reach a minimum of about 1100 degrees C. So that was some preliminary work that we did with these steel samples or the steel evidence that Steve was able to get from various people. In fact, one of the samples came from Clarkson University. Some of the steel beams had been sent out to Clarkson College, and they were going to build a monument with these, and there was a lot of debris that was sent with the beams, and some of that evidence came from that debris as well as coming directly off of the steel columns. So that's where these initial samples came from. Obviously, it required polishing these pieces of steel and then putting them in the electron microscope to find, and using X-ray analysis to find the chemistry. I used diffraction to determine the phase or the structure of the phases along with the chemistry. And then in that way we were able to determine the phases that were in the steel or in these pieces of steel that had been corroded or melted, whatever the process they had gone through. That's what we were trying to determine by looking at the phases. So again, we found that the phases that were there probably would require about 1100 degrees C. And that didn't entirely wrap up that part of the study, but that was pretty significant findings. The question became, how do you get to those temperatures? Obviously, the question of how do you get to 1100 degrees C is significant because you don't get to those temperatures with scattered office fires or even jet fuel fed office fires. You get to maybe half that temperature. So that question of how do we get to 1100 degrees C, that became fairly important to me, and one of the things that obviously made me more motivated to look further into this. I don't know that I could really speculate as to. I mean, there's any number of sources of heat that could create that temperature, but certainly not jet fuel burning in open air in an office. I guess what makes these findings significant is, well, it's sort of the manner in which we found them, the way that the morphology, in other words, of the grains of these phases. You don't get these phases with an oxyacetylene torch or whatever torch you use to cut the steel. You don't get these phases existing together the way that we found them. So it's, I don't know, I mean, yeah, people might say, well, they cut up the steel, couldn't you create phases with a torch? Yeah, you probably could. I'm not going to deny that. I don't, I mean, that's, and if that's what, if that ends that investigation, then I think what has to happen is you have to be able to take a torch and show that you can create these phases. And so far, nobody's done that. So I don't know. I'm not going to say that you can't do that. We did find small amounts of aluminum in some of the specimens. More significant probably was the sulfur content that we found. In fact, in one piece, I found a pore in the steel that had pure sulfur embedded in the pore, which I thought was very strange. And so that's when I really started looking for sulfur and finding it in more abundance in some of these phases. So then, of course, the next question is how do you get the sulfur in these pieces of steel or in the debris, and that question is unanswered. There are possibilities for sulfur. I mean, any number of possibilities. There's a version of thermite called thermate, which has sulfur in the thermate too. And what the sulfur does is it's sort of like salt on ice. It creates a eutectic temperature, so it lowers the melting point of steel. and in that way it can cut through the thermate can cut through the steel or melt the steel more quickly than regular thermite. The finding of aluminum in these steel samples, or what used to be steel samples, also supports the theory that thermite was used to melt the steel. I would certainly love to get an official sample of the steel that we know came from a large piece of the steel. This was actually done by Jonathan Barnett. He was contracted with FEMA or by FEMA to do this, and he actually took some of the steel members and cut them up, and he selected some very significant pieces of steel. He found ones that had oxidation or sulfidization of the steel members. Some of them looked like they'd been vaporized, certainly melted, and he cut up portions of that steel at that point, or at the locations where he saw the sulfidization. And he found similar things. He found iron sulfide in one phase. He found that the sulfur phases, or the phases rich in sulfur, were attacking the grain boundaries of the steel, which is exactly what thermate would do. It would go into the grain boundaries first to attack the steel and then melt the steel as it did that, and create that eutectic temperature. His findings were significant in that he originally started with steel from Building 7, and his question was then, do we find the same things happening in steel from Buildings 1 and 2, Towers 1 and 2? And the answer to that was yes, they found very similar things to what they found in the steel of Building 7. And then the next question was, how much sulfur do you need to create these sulfur phases? He did some preliminary tests, and I think those were significant. And those are some tests that if I had the means, if I had the steel and the time, I would do these. I would like to do these tests. How much sulfur do you really need to create these sulfide phases, or these sulfur-rich phases? Some people have speculated that the sulfur could have been supplied by the wallboard or the gypsum board that was present in the buildings. And I believe that's calcium sulfate, so it is a sulfate-rich phase. However, in order for that to happen, in order for you to get sulfur out of the wallboard, you've got to heat up the gypsum board to high enough temperatures to dissociate the calcium from the sulfur. And then you'd have free sulfur and be able to, and then the sulfur could then attack the steel, attack the iron phase or the steel, and create these sulfide phases which go into the grain boundaries. But again, you've got to get extremely high temperatures to dissociate those two things. And then you'd have the temperature, and then certainly if you've got those temperatures, you've got the temperature to melt the steel. So this would require high temperatures, certainly higher temperatures than you get in normal office fires. So this is impossible to achieve in a normal office fire, even a jet fuel fed office fire. You wouldn't achieve the temperatures required to dissociate the calcium and the sulfur in order for the sulfur to then attack the grain boundaries of the steel and melt the steel. So this is probably one of the reasons they use wallboard, is that it's not going to dissociate in normal office fires and attack steel members that are part of steel frame structures. So this is certainly an experiment that could be done to see if you get the sulfidization and this attacking of the steel member by wallboard, by just putting the two together in high temperatures. Certainly an experiment that could be done, something that debunkers could easily do. I don't know why it hasn't been done, although I can speculate that it doesn't work. So we use wallboard to protect the steel. Historically, this has never been a problem, that wallboard dissociates and you have a lot of sulfur in fires attacking steel members. So a wallboard is actually there to protect the steel. So Jonathan Barnett's study, which I thought was very well done and quite extensive, is all documented by FEMA in Appendix C in their BPAT report that was May of 2002. Unfortunately, it was never used in the NIST report, and it wasn't really used in the explanation for how the buildings fell in the FEMA report either. So it seems that although the report was done, and it was very well done, it was never really used by the report to explain, or should I say that the questions that they brought up in that report, which are, how do you get that much, where did the sulfur come from? How much sulfur do you need to create these phases? And how do you get the temperatures required to create the phases? I believe in the report they put a minimum temperature of 940 degrees C to create the phases, and that's at the eutectic. So those questions were never addressed by either the report or either by Jonathan Barnett's report, or by the FEMA report itself, or by the NIST report. These questions were never addressed. And I think they're significant because you have to, I mean, you've got this evidence here. How do you get those temperatures? Where do you get the sulfur? These are things that we should be asking and people should be investigating. So around in 2006, Steve Jones was working on some other evidence that he had acquired, which was dust evidence. And one of the things that he was doing was going through that dust and with a magnet and finding spheres, microspheres, whatever you want to call them, and looking at those spheres and trying to get the composition of those spheres. It's a difficult task at best to try and determine the composition of these spheres, because in order to get the internal composition, you've got to somehow break these open, and fortunately he was able to find some that were actually broken open. At this time, Steve was working with a student at Brigham Young University, a BYU student, a physics student, and Daniel Farnsworth is his name, and together they were working on the electron microscope and using X-ray analysis to try and determine the chemistry of these microspheres. To be honest, when Steve told me he was looking through the dust, through these dust samples, I thought this was a fool's errand. I just thought, you know, this is a needle in a haystack. I didn't really think that they'd find anything significant, to be honest. I really didn't. And I was stuck, you know, I mean, so I stuck with working on these steel samples, which I thought were significant, and I still do. Eventually, Steve came to me and said, we're finding these red-gray chips. And I really didn't think anything of it. It could have been, they could have been anything. And, but he kept, the significant thing about the red-gray chips was not just the frequency in which they were finding them, but also they were attracted by a magnet, and which was his method for pulling out these spheres. And so he was pulling out the spheres as well as the red-gray chips. And so he came to me and said, we're getting some interesting compositional analysis from the red layer of these red-gray chips. We're actually seeing peaks of aluminum, as well as other things. But the aluminum peak was significant because so he'd find these aluminum peaks, and as well as iron peaks, and oxygen peaks, and various other peaks. But the aluminum and the iron and the oxygen together were very significant because this is your composition for thermite. So that's when I started to get a little bit more interested in the dust and get more interested in these red-gray chips. So, but I didn't really start working on these red-gray chips, and Steve and Daniel were continuing to find things about the chips, and they would bring that information to me. And eventually I said, okay, I remember we were sitting in my office and he was talking about the red-gray chips. And I thought, okay, if you really want to see if these red-gray chips are significant, what we could do is take one of these chips and put it in a calorimeter and see if they're energetic. And at that point Steve was saying, well, how do we find a calorimeter? Who's got a calorimeter? So I found a lab that had a calorimeter that we could use. It's a DSC, differential scanning calorimeter, and learned quickly how to use the calorimeter and how to calibrate it and make sure that we were doing everything properly. I actually had somebody that really uses it a lot there with me as I conducted these experiments. And So we put one of the chips, one of the larger chips that we had, into the calorimeter and let it run to see what would happen. And that was really a turning point for the red-gray chips for me, because we got a peak on the calorimeter which shows that these red-gray chips were energetic. They were putting out more energy, and I mean they were very exothermic. And the width of the peak was also significant, because it showed the power that the chips had, and so that was really the turning point for the red-gray chips. And that's when I got very interested in the red-gray chips and joined them in their study of the red-gray chips and really took off with that. So that was, but the significance of the calorimeter cannot be understated here. The calorimeter can't lie to you. If that thing pops off, if you get a sharp peak in the calorimeter, that material is energetic, and the degree to it, the degree of its energy is determined by the height of the peak, and the power at which it goes off is the width of the peak. But we were finding very narrow peaks and very high peaks in the calorimeter, which showed that this very, very small chip had a lot of energy packed into it, more than you would find in everyday materials at the office. So, and certainly the number of chips that they were finding in these random dust samples made the fact that the fact that they were present there in such quantity also made them significant. So it wasn't an anomaly. It certainly wasn't an anomaly, because we were getting multiple dust samples from multiple individuals who had no connection with each other, had no connection to Steve or myself, and they're sending us these dust samples, and every one of the dust samples was showing red-gray chips, and they were. It was striking in their similarity. The paper that we wrote about the red-gray chips, you can actually see we've taken images of these photographs of these red-gray chips to show these things are so similar. We couldn't ignore these red-gray chips any longer, and that's where the paper really took off. That's where the data for the paper really took off. Some have speculated that the red-gray chips are just paint. I haven't seen any studies of paint by those that are speculating this. We did our own study of paint in the DSC and found that the paint will eventually burn up and turn to ash, but it certainly doesn't give you an energetic spike in the DSC. So we actually did some experiments to compare the elemental composition of primer paint from the Trade Center steel that was taken off of one of the beams in the Clarkson College beams. But it was taken from one of the beams used in the World Trade Center, and the chemical composition did not match that of the red-gray chips. So we know that it's not the primer paint that was on the steel. So once the chips were ignited in the DSC, we then looked at the residue or the remnant of those chips in the microscope again, and we did find very, very small spheres that were similar to the microspheres that Steve was finding in the dust samples. Smaller on average, but still very similar in composition and in look of the microspheres that Steve was finding. So one of the things that I'll just mention briefly, or maybe not so briefly, about the paper that was written that compiled all of this data from the red-gray chips. The first thing that we wanted to do was to establish that all of the chips were similar, and that and when I say all of the chips collected from the different dust samples that were collected from different areas in Manhattan, from different individuals who were not associated. So once we collected different chips from the different samples, we then took photomicrographs as well as looking at them in the scanning electron microscope, and then compositional analysis of both the red layer and the gray layer. And all of these things showed that these red-gray chips are the same. The compositional analysis of the red layer was the same. The compositional analysis of the gray layer was the same. Their appearance and cleavage habit or microstructure appeared the same. All of those things appeared the same. Then we ran multiple samples through the DSC, the differential scanning calorimeter, and found that they behaved almost identical. The peak heights were very similar. The location of the peaks were exact. And so once we were able to establish that these things were all the same, that's when we were able to then, with more confidence, try and determine what these things really were. And so now what we have is from the composition of the red layer, we have an aluminum peak, we have a silicon peak, we have the iron and the oxygen, as well as other peaks. And one of the things that we did to ensure that we weren't getting surface contamination was we just took some of these chips, which are very, very small, by the way, and under a microscope we were able to cleave these chips or break them in half and then study the fresh or the broken surface so that we weren't getting surface contamination. These things were coming in bags of dust, so who knows what kind of contamination you get on the surface. So we were looking at these broken or these clean edges in order to get the composition. And that's where we found the silicon as well as the aluminum peaks and the iron and oxygen peaks in abundance and throughout all of the red layers in all of these chips. The gray layer was also interesting. We found that was mostly iron and oxygen. And again, each gray layer was identical in its compositional analysis as well as its appearance. And then what we found from the DSC, there was actually some significant findings in the residue. After igniting these chips in the DSC, we found microspheres that were very shiny in appearance. Some of them were almost glassy, a little translucent. And we found that the composition of these microspheres, of these very small spheres, many of these spheres had the exact or identical composition or very similar composition as the spheres that Steve was finding in the dust samples. They were also very similar to spheres found in thermite, in commercial thermite. Once you ignite commercial thermite, you also get microspheres. And the composition was very, very similar. And that led to the conclusion of the paper, which was, we've got some form of thermite in these red-gray chips. And I think it's a very, very strong conclusion. There have been some that have argued that these red-gray chips could be paint of some form. We actually did a study on some epoxy paint. We put that in the DSC. We found that paint would just burn up and turn to ash. So you may get a minor exothermic peak, but it's not energetic. It's a very smooth, wide peak, and it's certainly not an energetic material. As part of the residue of the paint that we ignited in the DSC, the actual paint, it was basically ash. There were no microspheres found in the paint sample that had been ignited in the DSC. We also took paint that came off of the WTC steel and looked at that in the SEM and did a compositional analysis of that and found that it was not similar to the red-gray chip or the red layer of the red-gray chips. So it wasn't, the red-gray chips are not the primer paint that was used on the WTC steel. There are a lot of questions that came up during the paper that have been left unanswered or that are unanswered and need to be answered. Just an example, what is the gray layer? What was the purpose of the gray layer? We know it has a lot of iron, we know it has a lot of oxygen, and we've found that we do see there's a hematite phase, but there are other phases present in that gray layer, and we don't know quite what that gray layer is or how it's adhered to the red layer. Certainly further study needs to be done. We certainly need to be doing more work to find out what that is. Occasionally we would find an intermediate layer between the red layer and the gray layer, which was rich in carbon, perhaps a polymer type layer. But again, we need to go further with that study to figure out what those things are. There are some characteristics of the red layer that are rather significant. One is that it's not homogeneous. There are different particles or grains within the red layer that we studied. One appeared very bright under backscattered electron microscopy, which indicates a heavier phase. And we looked into those small particles. They were rhombohedral in shape and very consistent throughout the layer. They were about 100 nanometers in size, roughly, and very consistent in both their size, the shape of them, and as well as the composition that we could get from the SEM. Additional studies in the TEM found that these were iron oxide phases. So these particles, these small bright particles, they appear bright in the SEM images in the paper. These were, in fact, iron oxide phases that we were able to pin down using the transmission electron microscope. There were other phases present as well, or other particles present in the red layer. There were some plate-like phases or plate-like particles, and those, again, those were consistent throughout the red layer, throughout all of the samples that we found. And those appeared to have a higher aluminum and silicon peaks in their compositional analysis. And one of the significant things about what we find in the red layer is the fact that these particles that we find in the red layer are the fact that they're consistent, and the fact that, I mean, consistent in shape and in composition and in size leads me to believe that these things are not naturally occurring materials. The red layer is not a naturally occurring material. Sure, you have iron oxide everywhere. That you have iron, you get an iron oxide. But you don't get them in nice little 100 nanometer rhombohedral shaped particles inside of inside of a red layer, a very small red layer. And by the way, these, just to give you a reference on the size, these particles that are in the red layer are thousands of times smaller than, say, the width of a human hair. So these are very sophisticated particles, very sophisticated materials, not materials that we would expect to find in the demolition debris of a building. In order to get that kind of consistency with shape and size and to be that small, these really are sophisticated materials, and probably only developed in a laboratory. They may be processed outside of a laboratory, but they're developed in a laboratory. There were several other things that were found that we put into the paper that I think are very significant, and the conclusion of the paper really does fit well with the data that we collected. Our conclusions were that the red-gray chips are some form of thermite or a nanothermite or an energetic material which is very similar to thermite. And those conclusions are it's a very strong conclusion given the data. Now others may say, well, could it be something else? Certainly. It certainly could be something else. I'm not about to say that we've completely ruled out everything. But the conclusions we made in the paper are very strong given the data. If there's another possibility, that's something that somebody can come forward with using the same very stringent scientific method that we used in this paper, and publish that, and they'll find, I can guarantee they will find that our work is completely reproducible. If you find other red-gray chips, they will look and have the same composition and the same behavior in the calorimeter as the red-gray chips that we found. Now, if they come up with different conclusions than we do, that's their prerogative, of course, and I'd like to see that. I'd like to see other people looking at these things, because that reproduces our results, and it also brings us to a discussion which needs to happen. We need to be talking about this. There needs to be another investigation of the events of that day. And that's why I signed the petition at A&E, at the A&E website, A&E for 9/11 Truth, Architects and Engineers for 9/11 Truth. That's why I signed the petition, and I do believe there needs to be another investigation.